Okay, so now that we have seen the degraded uh, broadcast channel capacity in the case of the memoryless, discrete memoryless case, we focus on the Gaussian case. Gaussian case, the degraded broadcast channel, well, let's say the scalar uh, Gaussian broadcast channel turns out to be stochastically degraded in the following sense. So first of all, how it works? Well, it's simply uh, two Gaussian additive noise channels with the same common input. So we send X, and then receiver 1 receives G1X plus Z1, receiver 2 receives G2X plus Z2, and in the real case, we consider everything is real. Z1 and Z2 are identically distributed noises with the variance n0 half. We define the SNRs in the usual way. Received SNR by user 1 is SNR1, 2 times G1 square ES is the energy per symbol here, so we constrain X to satisfy this input power constraint, and SNR2 will be the same for user 2, and without loss of generality we can assume that SNR1 is greater or equal than SNR2, otherwise we reverse the role of the two users, so user 1 is the better user, user 2 is the worse user. And this channel, of course, we have also the circular symmetric complex version, which is defined as usual, where everything is a circular symmetric complex. This channel is stochastically degraded in the following sense. Suppose that user 1 is the better user, so he has a larger SNR. So what user 1 can do is to take its own input, scale it by G2 over G1, and then add some independent noise, call it delta Z. So what we get is G2X plus G2 over G1 Z1 plus delta Z. And now we see that we can simply, so the variance of this thing here would be G2 over G1 square times n0 half plus, let's call it delta n, the variance of delta z. We can, since G2 over G1 is less than 1, we can find a positive delta n such that this is equal to n0 half. That's easy. And it turns out that therefore this noise is stochastically equivalent to Z2. So I can call it Z2 tilde has the same distribution of Z2. This has the same gain of user 2. So after this scaling and adding noise, user 1 can simulate or emulate stochastically the output of user 2. Therefore, we have the stochastic degradation. So that's important. Of course, there is also the physically degraded version of this channel would be the input X, then we have the first gain and noise, and we get y1, and then we have exactly what I said. We have another multiplication by G2 over G1 and adding extra noise, and here we have y2. Okay, So in this case, this would be the physically degraded version where we have effectively a random transformation, which is a degradation because it's a scaling, attenuation plus extra noise, such that y2 is effectively a physically degraded version of y1, and we have the Markov chain x, y1, y2. So you always see that every time we have stochastic degradation, there is like a physically degraded version of the channel with the same capacity region. So we have a theorem that says that the capacity region of the Gaussian broadcast channel is given by this expression, this region, R1 less than, so remember that the function C of SNR is 1/2 log of 1 plus SNR in the real case and log of 1 plus SNR in the complex case, where SNR has the correct definition. SNR in the real case has a 2 here, SNR in the complex case has no 2, and has magnitude square of the G, because the G may be complex. So that's a formula that holds for both cases. And the capacity region is the region obtained by rates satisfying these inequalities for any alpha from 0 to 1. So in other words, you see, you let alpha equal to 1, what happens? We have R1 less than C of SNR1, which is the individual capacity of user 1. Let alpha equal to 0, well, so we have a point here, because for alpha equal to 1, then C of 0 is 0, so R2 less or equal than 0. So we have a point on this axis. This is axis R1, this is axis R2. Let alpha equal to 1, so let alpha equal to 0, so now R1 less or equal than 0, so we are here on the vertical axis, and R2 less than, we have SNR2 divided by 1, because alpha is 0, so we have the capacity of user, or individual capacity of user 2. And then as you let alpha vary from 0 to 1, we have a contour that looks, no, it's not a straight line, it is a curved contour that looks like this, okay? So the region is always convex because well, because it's a capacity region, and we know that capacity region, you can always convexify it. In this case, we don't need to take the convex hull because this region is already convex. So the convex hull of this region is the region itself. And we can see that in general, orthogonal axis is strictly worse. If you take the segment joining these two lines, it's strictly worse than this capacity region. So to prove this theorem, we have to prove two things. Well, first of all, the achievability, we have simply to particularize the general achievable region for the degraded broadcast channel to this Gaussian case, and this is obtained by basically picking the auxiliary random variable in and you know the joint distribution of u and x in a convenient way. But most difficult is to prove the converse, because the converse that we have for the discrete memoryless case, the general case, is, you know, it says that, well, we have this mutual information, but this is for some distribution. But here we have a precise expression. We have to somehow also prove that that choice we make in the achievability also exhausts the converse. So this is in fact the converse and achievability coincide. So let's see how it goes for the achievability. For the achievability, we use this choice. We choose the auxiliary random variable u to be Gaussian. To be Gaussian with variance 1 minus alpha times ES. And then we choose x given u to be conditional Gaussian with mean u and variance alpha ES. So we have, the density of u is a Gaussian. The conditional density of x given u is a conditional Gaussian, where the conditioning is only in the mean. The variance is fixed to be alpha ES. Now, here you understand why this coding technique is called superposition coding. Because basically what we are doing here, we are generating points u according to this Gaussian IID distribution. So those are Gaussian random vectors in n dimensions. And then for every point u, we are creating, so imagine, we have, this is u in a high dimensional space. And then we are creating our auxiliary codebook by generating additional vectors, let's call them v, with a Gaussian distribution with mean 0 and variance alpha ES, such that when we sum them together, x becomes mean u and variance per component ES. So that's why it's called superposition coding. We really have a code book that looks like this. We have generated these Gaussian random vectors u, which are essentially points in an n-dimensional sphere of radius square root of n times 1 minus alpha ES. And then for each one of these points, we have generated a cloud of points around. Let's change color so you see them. And this, again, is a sphere with radius square root of alpha ES. At the end, since these auxiliary vectors are independent from the center clouds, the variance is sum, and so the overall variance per component will be, alpha ES plus 1 minus alpha ES is going to be ES. So we are going to generate all this center cloud here, or these clouds like that. Okay. So this is really called like superposition coding, because you can effectively construct the encoder in the following way. We have message M2 is encoded into a sequence UM2. We have message M1 that is going to give you VM1, and then we simply superimpose them, so we send the sum. So the X M1 and 2 is simply the sum of the two. U M2 plus V M1. Okay? This is the geometric intuition in the Gaussian case, and this is the origin of the term superposition coding for the general coding technique that we have seen by generating cloud centers and then generating auxiliary codebooks around each cloud center. Okay, so basically the choice at the end is that the distribution of x and u is jointly Gaussian, because pu is Gaussian and px given u is conditional Gaussian, so the overall distribution is jointly Gaussian. Okay, so if you do this and you particularize the rate region let's do it here. It's very simple. In general, we have R1 less or equal than mutual information between X, Y1 given U, R2 less or equal than mutual information between U, Y2. So let's simply calculate these mutual informations in this Gaussian case. So what we have? Let's start with R2, which is easier. So mutual information of U and Y2, but Y2 is what? Y2 is G2X plus Z2. But we say that X is U plus V, where V is, this is Gaussian 1 minus epsilon ES, and this is Gaussian 0 alpha not epsilon ES. So I can simply rewrite this as the mutual information between U and a new channel with input U and a sort of noise G2V plus Z2. I count this as noise. This mutual information, notice that V and Z2 are independent of U, so this is exactly a Gaussian additive noise channel whose capacity is 1/2 logarithm of 1 plus. Now the SNR here is going to be the variance of our signal, which is 1 minus alpha G2 square ES divided by the variance of the noise, which is N0 for the Z2 plus G2 square alpha ES, right? And if we remember, the definition of this thing was a 2G2 square ES divided by N0, and the definition of this one is 2G1 square ES divided by N0. So you see from here that if I simply multiply numerator and denominator by 2 over N0, I find exactly 1/2 log of 1 plus. I have 1 minus alpha SNR2, 1 plus alpha SNR2. Okay? So essentially, user 2 treats the auxiliary vector, so the cloud points, as additional noise, and decodes only the center clouds, because its message is somehow encoded in the center cloud, so in the variable U. Okay, so we have calculated these mutual information. So we have proven the first, so the inequality for R2. Let's look at the inequality for R1. So I'm going to add a page. For R1, we want to calculate the mutual information between X and Y1 given U. But this mutual information, so let's see what Y1 is. We have X, Y1 is G1. Again, I write this as U plus V plus Z1 given U. And now I can write this as, okay, I can do it quickly and say, okay, U is conditioned, so this is a constant. So this is the same as the mutual information between so this should be U plus V, U plus V. Okay. So this is the same as the mutual information between V and G1V plus Z1, which is 1/2 log, and this is again a Gaussian additive noise channel with SNR equal to simply alpha SNR1. Okay. If you don't see it immediately, we can go through the differential entropies and write these as the the differential entropy of the output G1 U plus V Z1 given U minus the differential entropy of the output given U and U plus V. And now you see that here, this condition here, so this is just the differential entropy of G1V plus Z1, which is independent of U, so I can remove the conditioning, minus, and here this sum makes this constant, so this is just the differential entropy of Z1. And now these are all Gaussians, so this is 1/2 log 2 pi E times the variance of this thing, which is G1 square alpha ES plus and 0/2, and then minus 1/2 log 2 pi E and 0/2, and then we get the same formula. Okay, we put things together, we get the same. Okay, so this shows that if we take the general formula for the achievable region with superposition coding and we particularize for this special case with this choice of Gaussian U and X, we end up with the achievability of this region. This is true for every alpha, so you just let alpha change and you have a whole, you describe the boundary of this region. So as I said, the difficult part is to prove the converse, because here we are dealing with the continuous alphabets. So cardinality bounds have no meaning. So what we have to find is a converse that shows that this particular choice of P, U, and X jointly Gaussian is in fact optimal. And this goes beyond the general converse, because in the general converse, we do not know how to choose the auxiliary random variables. So we have a particular proof, Gaussian converse, that works a little bit differently. So we need to show that basically for any choice of auxiliary random variable U such that U, X, Y1, Y2 form a Markov chain, so for any joint distribution of the form P, U, P, X given U, P, Y1, Y2 given X, there exists some alpha such that this is true. So in other words, the region we have found contains all possible regions coming from the converse. The converse says the converse region is, you know, is the union over all possible such distribution. But here in this case, we have to we are going to show that for any such distribution, the corresponding mutual information are inside, are dominated by the one found for the Gaussian case, which is what we have just proved before. So it turns out that it is useful in this case to work with normalized channels that is simply obtained by rescaling the output such that we have gain 1, you see here and here, and at this point the noises will have different variances. Let's call it N1 and N2. simply obtained by scaling the output of user 1 by 1 over G1, scaling the output of user 2 by 1 over G2. Okay, so in this case we are like this, and by the assumption that G1 is greater than G2, so we have the order of degradation, N1 will be less or equal than N2. So the user 1 has a better channel because it has less, has noise with smaller variance. So here, in addition, we also choose to consider the physically degraded case in which the output of user 1 is this, and the output of user 2 is obtained by basically adding noise to the output of user 1. And the noise, because after the scaling, the noise has simply the variance equal to the difference of these variances. So at the end, Z1 plus delta Z has the same variance as Z2. Okay, so that's the physically degraded case where we really corrupting Y1 by adding noise and getting Y2. So in general, we can start by taking the mutual information U and Y2 for any distribution. So we are looking at the general distribution of this form. Okay, so every time I write mutual informations will be with respect to any distribution of this form, and then we will show that for any these inequalities are true. So given a distribution in that form, we have a mutual information I, U, and Y2, and this is always, I can always write this as H of Y2 minus H of Y2 given U, okay? And because of the Gaussian bound on the differential entropy, I can write that for any Y2, the differential entropy of Y2 is less or equal than the Gaussian differential entropy of for the same variance. And what is the variance of Y2? Well, the variance of Y2, we see it from here. The variance of Y2 is simply, well, Y2 is X. Y2 is X plus Z2, right? And so the variance of Y2 is ES, which is the variance of X, plus the N2, which is the variance of Z2. So this is the Gaussian differential entropy, and this is simply this term. We don't know this term, and this is a problem, is to bound this term, but we have this bound. Second, what we can do is to take this differential entropy, write Y2 as X plus Z2, and adding this conditioning, right? If we add the conditioning on X, conditioning reduces differential entropy. At this point, adding the conditioning on X makes this differential entropy equal to the differential entropy of Z2 alone, which is independent of anything else, which is Gaussian, and therefore we have that this differential entropy is some number lower bounded by the Gaussian differential entropy of the noise Z2 alone. Okay? Also, the differential entropy of Y2 given U is less or equal than the differential entropy of Y2, which we have already upper bounded in this way. So we find that this term, for any distribution, this term is in between 1/2 log 2 pi e n2 and 1/2 log 2 pi e es plus n2. Okay? So since this is in between, there must be some alpha, for which we have equality here. Because look, for alpha equal to 0, we get the lower bound. For alpha equal to 1, we have the upper bound. Logarithm is a continuous function, so there must be some intermediate alpha for which that achieves equality. Okay? Then we can write the following. For that specific alpha, replacing this term with this equality, replace it in here, and using this inequality here, we put things together, and we arrive at the fact that for that specific alpha, I of uy2 is less than this quantity, which is the first inequality we want to prove. So there exists an alpha for which this is true. But the problem now is to prove the inequality for the other for the other mutual information. So to prove this inequality, and this alpha must be the same, because that's the same alpha. So in order to do this, we use again the entropy power inequality that we have already encountered a couple of times in this course. And in particular, we use a conditional form of the entropy power inequality that works like that. Given xn, zn to be conditionally independent given another random variable u, with densities px given u, pz given u, and letting yn random vector given by the sum of the two, it turns out that the entropy power inequality works also for the conditional entropies. Normally, if you remember, we have stated, not proven, but stated the entropy power inequality without the conditioning, which was like this. But even if we look at conditional distributions and conditional entropies, the entropy power inequality holds, and it holds with equality if xn and zn are conditionally jointly Gaussian. Okay, in the conditional jointly Gaussian case, we have equality. So in our case, well, n is equal to 1 because we have only single letter expressions. So we have the y2 is y1 plus delta z, and y1 and delta z are conditionally independent given u. Why is that? Because we have our underlying distribution is pu px given u, py1 given x, and then we have py2 given y1, right? This is for the degraded case, right? And it turns out that when we fix u, basically all the dependency on u is in y1, and when this is fixed, basically y2 only on given y1 is an additional independent Gaussian noise. So this means that if I apply this inequality in this case, I have that because y2 is y1 plus delta z, and delta z is Gaussian, we have 2 to the 2h y2 given u is greater or equal 2 to the 2h y1 given u, which is the first term, plus, here it should be 2 to the 2h delta z given u. Delta z given u is the same as delta z because u has no influence on delta z. Delta z is Gaussian, and therefore this conditional entropy is simply, 2 to the 2 times 1/2 log 2 pi e times the variance of delta z, which is by construction was n2 minus n1. So we end up with this term. Okay. So this is the entropy power inequality applied to y2, written as y1 plus delta z. Now, using the entropy power inequality, remember that for that alpha for which this differential entropy is equal to 1/2 log 2 pi e alpha es plus n2. We replace this here. We have that 2 pi e alpha es plus n2 is greater or equal than this term that comes from here plus this term that comes from here. And so putting everything together and expressing the inequality in terms of the h of y1 given u, we find this upper bound on the differential entropy of y1 given u. And finally, we start with the mutual information we want to bound. We write it in this way. Now we have that given xu y1 is just a z1, so this is just the Gaussian differential entropy, and then we have just proven the bound on h y1 given u, which is this. We put things together and we find exactly what we want. So we have proven also the second inequality. I mean the first, in the order of the way they were expressed here, the first inequality. Okay, so both inequalities are proven, which means that if I pick, since these two terms, and these terms, are these mutual information for the choice x and u jointly Gaussian, then this shows that this choice of the auxiliary random variable and the x given the auxiliary random variable u, in fact, exhausts the whole capacity region for the Gaussian case, because for any possible distribution generating these two mutual information, well, this is inside the corresponding boundary for the Gaussian choice. Okay? So this essentially proves the optimality of the Gaussian inputs for the Gaussian broadcast channel. So I guess we can stop here, and in the last part we are going to give a few more results on fringe extensions and other classes of broadcast channels for which superposition coding is also optimal.